Okay, let's give you guys some more practice. So in the past, we've seen that in terms of motion, y could represent displacement, time, and if you differentiate it, the derivative happens to represent velocity. If you differentiate it again in terms of motion, it represents acceleration. And then when given the acceleration, you can integrate it, and then it will take you back to velocity. If when given the velocity, if you integrate it, you will get the displacement. So in economics, these dy by dx and the second derivative here will have some sort of meaning associated with it. But in terms of motion, it represents displacement, velocity, and acceleration. In economics, it will represent, it will have some sort of meaning associated with it in economics. Okay, so in this video, I'm going to give you the third derivative. So in this video, I'm going to give you the third derivative, and your job is to integrate it, and then integrate it, and then integrate it to get to your displacement. Okay, so the question here is, given the third derivative equals 6 here, these are your initial conditions. Find y of 10 here. Okay, so what's been given here? Hang on. So the third derivative being 6, the third derivative equals 6. So your graph will look something like this with 6 here. But the thing is, when you integrate it, you will get to acceleration. You will get to acceleration. But the thing is, when you integrate this here, you're going to get a whole family of these. You get a whole family of lines with a gradient of 6. So, but you see, you can use your initial condition here to identify the precise line that you're interested in. Maybe this one here, because it's saying that when y equals 0, it will be -2. So here the intercept here is -2. Okay, so the initial condition here helps you to identify which line you're interested in. Okay, so when given a straight line like this, if you integrate it, in terms of motion, it will represent acceleration. Now, integrated again, it will represent, in terms of motion, it will represent velocity. But the thing is, when you integrate this here, you're going to get a whole family of these lines here. But then you're going to get a whole family of these lines here. But by using your initial condition here, you can identify which line you're interested in, because when y equals when this is 0 here, you can use your initial condition here to identify the one you're interested in. And then if you integrate it again, if you so here this is your velocity. Integrate it again, it will integrate it again, and it will give you a whole family of these type of graphs here. But then you can use your initial condition to locate the precise line that you're interested in. Okay, so hang on. So in terms of motion, so you can think of this as being like you sitting in a car here. Okay, if you put your foot on the pedal, you will register an acceleration. So if you put if you put your foot on the accelerator, your car will accelerate. So your acceleration, your acceleration will register an acceleration. Your velocity will increase as time goes on, because if you accelerate, it means your velocity increases, and then it turns out that the distance you travel will be something of this nature here. But the thing is, if you're sitting in a car and then you put your foot on the pedal, you will register an acceleration, but you will not register the third derivative. So your third derivative graph will look something like this. It will not register anything. You see, you will register something if another car crashes into you. Then you will register something here. You will register a third derivative. Okay, so this third derivative, you can think of it in terms of motion. It's a measure of what's called jerk. It's a measure of jerk. But don't worry about it too much. So hang on. So here, find this here. Okay. So given the third derivative equals this, these are your initial conditions here, and find y, find 10 of y here. Okay. So press pause and have a go, and then I will tell you the solution in the next video. Okay.